Okay, hello. Welcome. Are you recording?
I should be recording.
Okay.
I guess it's good to check. Mm. Wait, am I what? Okay, I'm recording. Yeah.
Okay, cool. All right. Hello and welcome to the Lab 4 Health session. I'm Davis.
I'm Daphne.
And so we're just going to be going over some basic principles that are used in Lab 4, as well as how you can go about using some of the features that you'll learn in Lab 4 later on in the course.
Yeah, so we're doing a practice problem over how to design an ALU. I'm going to explain kind of like how the RALU works in a general sense. We're going to do practice for making table 4, which probably should have seen in class, but just go over it again. We're also going to go over shift registers and some tips on using the DAD for I think part 2 of the lab.
Yeah.
So let's get started. Okay, so let's start off with like the concepts behind like how an ALU works. So let's say we have two inputs, which are the bus A1 through A0, and we have B1 through B0. So it's four signals total, but we're grouping them together into two buses, and we want to be able to perform two different operations on them. And so here is the select bit, which you'll see we literally put into a multiplexer to determine which one of these functions we do. If that select bit is 0, then we want to output not A. So we want to output like a bus of A1 not and A0 not. And then if it's 1, then we want to do A1 or B1 and A0 or B0. And so the way this works is we want to be able to select which function we're doing, right? So we probably want to use a multiplexer. Let me draw that out. We only have one select bit. If you wanted to do more operations, you'd have like more than one select bit. So this is S, and then S0 goes into it. And then going into this multiplexer, we have two inputs because this is a like one select bit mux. And we have our output. Um, and the output is going to F1 and F0. So we're actually going to need two multiplexers. We will need one like different multiplexer for each time, like for each individual output bit. And you also see for the operations, like you need to have separate gates to perform these functions, like a different one for each bit. And I'm saying this because in Quartus, like it'll let you put buses as inputs into like a multiplexer or whatever, like you might try to put a bus into like 74153 and it just won't work. So you have to have a different one for every single bit you're doing, but you do have the exact same select bits for both of them. And so let's say that this one outputs F1 and this one outputs F0. And I'll draw the inputs for these. And so let's just start by thinking about like how are we going to implement these functions? Well, like this is very simple to implement. It's literally just we have a NOT gate of A1. I'm doing this now, sorry, this is kind of bad, but we have A1 to not A1. And then we have A0 to not A0. And like some of the functions you might have to implement will only use one register. Other ones won't, like, sorry, not a register yet. Some of them will only use one input, some of them will use both. Like, it doesn't matter as long as you have like one bit that corresponds to F1 directly and one bit that corresponds to F0. And so I'm not going to draw all of it for S0 equals 1, but this is like what one of the bits looks like. So this is A1 or B1, and this will correspond to F1. And so let me just label these like you're probably going to want to come up with a good like internal label name for these. So like in Quartus, you want to have the output of this signal be some label so that you can connect it to these multiplexers over here. Um, so let's just say that this one is not 0 and this one is not 1. And that's not a very good name because like for example, if you wanted to do like and 1 and 2 or something, like it would probably overlap, but like you can come up with whatever descriptive name you feel is apt. And so going back to the multiplexer, if this input is A and this is B, and let's say that S0 being 0 outputs A, S1 being 1 outputs B, then what we're going to do is, and let's say this is or 0. I know that is a bad name. Please don't make something like that. But like, so what we're going to do is we know if S0 is 0, then we'll output not A. So let's put not 0 into like literally when S0 equals 0, and then or 0 into the B output, so when S0 is 1. And then here we can do the same exact thing, except that, oh, my bad, I mixed up the numbers. So this should output like our equivalent of not 1 and or 1. And this one should output our equivalent of not 0 and or 0. And so like you're not going to have to do any more complicated logic than this for your ALU. Obviously, you're going to have more multiplexers and more like circuits here. Like you would have, instead of 2 of these NOT gates, if you wanted to do like a 4 input bus for A, then you would have to have like 4 individual of like things like this in Quartus. But this is logically how it is all put together. So let's see. The next thing I wanted to go over is like,
Yeah, go ahead.
sit down real quick. I want to explain what is going on in like this block diagram of the RALU. So let's see. So this part you can think of as its own like little ALU. Like if I draw it out here, if this is mux C, and this has like, you can't actually like design this with the buses, but just for the sake of time, this is S2 to 0. Then what's going into this mux is the combinatorial logic. So this is like the same as the little gates we designed before. So like you might have like something from register A being knotted, and that output goes into one of these lines for the mux. So I have not and or whatever. And it just so happens that the thing that you are putting into this multiplexer, like this ALU, is from a register. And each register is literally just a collection of D flip-flops. In this case, we have 4 D flip-flops. So, or we have 4 things in the register. So we need to have 4 individual flip-flops for each bit. And so, like, I guess my point is that you've already designed how the ALU works. You might have to expand it to implement like more functions with the bigger mux, but when you get to the RALU, you've already designed the ALU part. And so what you have to do on top of that is add the registers in. And let's see, I kind of wanted to talk about the motivation for using the registers. You want to be able to control when new data is passed into like this combinatorial logic section. You're controlling the instruction not just by changing what's in MSC, which is like the actual operation being performed, but you also need to change MSA 1 and MSA 0 because these select which one of these buses output register A input is going into the register. So basically, since you're able to store different things into the register that goes into the ALU, you're able to do different things. So the MUX, like MSC, might have like it might have an operation that is nodding every single thing going into it. But based on whether MSA1, MSA0 is taking input from what's from whether it's taking something from input, you might that would be just sorry, like that would be nodding the input versus if you set register B to go into register A, then it did that function on this register, then you'd be performing a different operation. And so that's where I kind of get into like the idea of a control word. A control word is a collection of zeros and ones. We might write them in this sequence. They're being like put into different locations in this RLU. But what you're going to see with your dad is you're going to represent this as a sequence of bits. And so to these bits, I'm not putting in like meaningful values here, but just so you can see, like to these bits represent which bus is going to register A. Two of them represent what's going into register B. And three of them represent the operation being performed on register A or register B. The combinatorial logic might be what's determining which one of these registers is having the operation like performed on it. But in summary, this is a machine code instruction. And so what you're going to see when you go through the table is you have to write out the state of MSA, MSB, MSC while we're doing different things, right? You have to, like one column is going to be like, make MSA hold its value. And another column might be like, make MSB take input from the input bus. And then you have MSC's instruction. And so when you put them all together, that is like an instruction. Oops. And you'll see later on, there are ways to like, since this is a lot of different bits, right? There are ways to represent each instruction in fewer bits, but ultimately it's going to be translated into something like this, where you have bits multiplexing one register, bits multiplexing another register, there might be more registers, and then finally bits multiplexing the ALU part of it that is doing the instruction. Let's see, do I have anything else? And like just as a conceptual thing, the output bus, like this part, or I guess it would be more accurate to circle like this part is not related to the clock at all. So you need to change like instructions will take a certain amount of clock cycles to execute, but that is determined by the time it takes to put things in register A and register B to make sure that you are not like how would I say it? You want to avoid race conditions or just things being messed up by things not being synchronized. So the clock determines what goes into register A or register B, but you see when you do your table, like the output bus will immediately change as soon as like register A and register B change. So it's not a separate clock, I guess is what I wanted to say. Yeah. That's all I really had for this. I guess, did you want to go over table 4?
Yeah.
There's a really helpful document on the website already that like,
Yeah, so if we
Yeah.
just if I click it, will it go?
it should, you could, I can get it.
All right.
I'll probably just have to paste in my browser.
Okay, so if you go to this document, you saw where.
Sorry, do you want to, I should probably put on another screen.
Oh, yeah. Okay, so if you look at this document, so mouse? Okay. So if you look at this document, this is a little snippet of the table. So if you go to the actual end of the document, it'll have a full table for you. And we're going to see that more in the next slide. But this table has representation of like what's going on. And then this whole document like basically explains how you can think about it. This text is very useful. It might seem like a lot of yap, I guess, but read through it and it's actually going to help you understand. I'd say this diagram right here is what helped a lot when going through this lab because, like Daphne was saying before, the clock portion is actually what inhibits the data being moved. So if you look at this, our function of our output and our what is it called? The carry? Yeah. The function of the output and the carry is not dependent on the clock, but what the inputs are for register A and register B are dependent on the clock. So this whole diagram of being able to see what's going on is extremely important as you'll be able to actually figure out like how the program will work and how you can actually set up your table in the top. That's all I had for this. We can go. Do I need to give? Okay.
Okay. Okay. Okay, here's
Okay.
the practice example.
So, here, I guess I can sit. But I made a little table example. So this is actually going to probably take a minute, but this is a basic example and it's something that you could see in lab 4 and later on down the line. So another first thing I want to say is that this right here, the dollar sign in front of the C represents this as a hexadecimal number. So when he says that use input of $C, he's just saying input C in hex, which by now you should guys all know that how to represent letters in hexadecimal. And then input $C to register A, input 2 to register B, and then add both registers and store in B, and lastly multiply by 4. So if we go to the next slide real quick, we have this documentation here, which shows the mux select lines and its purpose, as well as the mux select C lines and its purpose. And we'll be using this in detail when going through this table. So the first thing that we want to do is actually input $C to register A. So we something that Schwartz wants us to do is whenever you are inputting some or whenever you're dealing with data in one of the registers, the other registers are supposed to hold. So register B, while we're inputting into register A, is just going to be 1 0, so that it will be referencing itself almost like a little like loop. And then what he also says is that if you're not doing anything with mux select C, you always have it default to 0 0 0. And this is just, I mean, you could have it be something else, but 0 0 0 is what we decided on. So input $C to register A. So $C, if we know hexadecimal, is 1 1 0 0, because C is 12. And if we look in binary, we have 1 2 4 8, and 4 plus 8 is 12. So our input for this first row is going to be 1 1 0 0. And then Cn for this whole table is going to be 0 because in the instructions don't tell us to use Cn. So we can just set this 0. And I might have more rows here than we need, but I'll just put it. So if you look at the table, so if we look next, so we want the input bus to go into mux select A, and we want B to hold. So input bus represents 0 0, and then hold is 1 0. And because we don't want to do anything with mux select C, we can just have it at 0 0 0. So currently, whenever we start the program, register A and register B are at 0 because they just initialize to 0. Or I guess you could also represent these as don't care, just because you have the chance of having garbage. And then output will also be 0 because the input, it starts at 0.
I think it would be better to put register and register B here as don't cares because like it's
Okay.
not known what these values are.
Yeah. So, eraser. Okay. So we can just put don't care.
Yeah.
Don't care. Don't care. Don't care. Okay. And then so for register A plus, after we clock the signal, the input will be moved from like, well, the input bus will stay the same, but it's going to be transferred into register A. So after a clock signal, we're going to have 1 1 0, 0 in register A. And register B will stay the same as don't care or 0. And then the output bus, because we're just looking at taking the input, and then we know that the 0, 0, 0 represents register A to output bus. So that means that register A will be outputted. And now for C out is always adding what's in A and what's in B. So at this moment, it doesn't matter what we're doing. Whatever is in A, whatever's in B is added to C out plus. So since we don't know what B is, and we know the first bit of A is a 1, I'm just going to put an X, but this will probably be a 0 because B will likely be a 0. But again, like Daphne said, we don't know what's in B. So now that we have C and A, we want to input 2 into B. So 2 in binary is 0, 0, 1, 0. And so we'll have that as our input bus. And if we want A to hold, that means we do 0, 1 according to the table. I just have it memorized. And then we want B to come from the input bus, so 0, 0, same like MSA. And we're not doing anything with MSC, so we're just going to have another 0, 0, 0. And now this time we don't have garbage. We know exactly what's in it. So, well, there's garbage in B, and the output bus is still 1, 1, 0, 0 from the previous instruction. And register A is 1, 1, 0, 0 because we just put it in there. And then now after the instruction, A will stay the same because we have it as a little infinite loop. B will be inputted as 0, 0, 1, 0. And the output bus will remain pointed at A. So it'll be 1, 1, 0, 0. And if we look, now we can actually check the C out condition. So if we look at the first bit of A and the first bit of B, it's 1 and 0. And 1 plus 0 is 1, which means that there's no carry. So our carry out will be 0. Now that we have these in the registers, let's add them. So if we look at mux select C, 1, 0, 1 represents adding the bits. So I'm going to keep, oh, and then we want to store it in B. So the output bus is 1, 1 for mux select B. So we'll have it as 1, 1 so that when it comes out the output, it'll be going into the input. So we'll have mux select B as 1, 1. We'll have mux select A pointing to itself, so it's just in a little loop. And then we'll have mux select C as 1, 0, 1, so that they're add. And then our input will just be 0 because we don't need to input anything. In fact, it can be 0 for the rest of the table because we don't input any more numbers. And then for register A, it'll stay 1, 1, 0, 0. And then for register B, we're going to add, it's still the same because this portion here represents before the instruction. So register B will just be what is in register B plus from the thing before. So 0, 0, 1, 0. And then the output will be a sum of these. So if we look and we do some binary addition, the first, I guess, position would be 0 plus 0 is 0. Then we have 1 plus 0 is 1. And then the rest of these 0 plus 1 is just 1. So it'll be 1, 1, 1, 0. And after the clock edge, we'll store that in B. So 1, 1, 1, 0. And A will still be the same. So 1, 1, 0, 0. And the output, we would add again these numbers. So the 0 and the 0 would add to be a 0. The 1 and the 0 in the second position would be a 1. Now, when adding two ones, so if I do 1 plus 1 in binary, we get 0, 1 because this is 2. And if we add 3 ones, so plus 1, 1, 1, you can think of adding these two right here as being 1, 0. And then we add in the third bit to this number, and we get a 1, 1. So if we look here, we're adding 1 and 1, which should give us 1, 0. So we'll have a 0, and we carry into the fourth bit. And then we have 3 ones. So we're adding 1, 1, and a carry. So our output will be 1 and 1, because we can only store this bit in 4 bits, the last one will be a carry, which means that the carry out will be a 1. Okay. And then we'll just go to the next line. So we can copy the reg A plus and reg B plus into the current values. So 1, 1, 0, 0, and 1, 1, 1, 0. And so now we want to multiply by 4. So if we look at the, let's erase this. So if we look at the value, a shift left is equivalent to multiplying by 2. Because if we have 2 to the 0th, and then 2 to the 1st, and then 2 to the 2nd, if we have a bit here, which represents 1, to multiply it by 2, we just shift it over 1 because we're increasing the exponent by a factor of 2. So a shift left, it would be this, 1, 1, 0. So this would be multiplying by 2. If we want to multiply by 4, we can just do this 2 times. So let's go back. And so now we want to do a shift left. But if we look back, we remember that this says shift left from register A. So that means that we need to transfer the data in B to the data in A. Now, a good question that you can have is, can we do this simpler? So yes, you can. So if I have this line right here, we can actually set MSA and MSB to 1, 1, so that when the data comes out, it will go into both register A and register B. However, just for simplicity, I'm going to do a data transfer method. So we want MSB to go to the output, and we want it to come into A as the input. So MSA will point to the output bus. MSB, we can just keep it as the same because we're not changing any data. And MSC will be the B, register B to the output bus 001. Oh, well, 001. So 001. Okay. And then, so now MSB will be at the output bus, which is 1110. And after the clock, it'll go into register A. So 1110 and 1110. So now if we do some more adding, bit 0 will be both zeros. Bit 1, if we add a 1 and a 1, which is going to be a 0 with a carry. Then we have 3 1s in bit 3, or well, bit 2. So it's going to be a 1 with a carry. And then if we look at it again, so we have 3 1s in bit 3, which means we'll have a 1, and then our carry out will be a 1. So now that we have the value in A, we can just copy these registers over here. So 1110, 1110. And so now we want to multiply by 2. So let me just check the documentation. Shift left is 110. So now we can just do 2 shift lefts. So 110 and 110. And we can keep B the same because we don't need to do any more operations with that. And we can have A come in from the output bus. Well, yeah, we want A to come in from the output bus. So it'll go back into A. And then we'll do the same for this row. So we shift left once, put it into A, shift left again, and put it into A. So if we have the output, a shift left is going to add a 0 in the beginning. So it'll be 1, 1, 0, 0. And B will stay the same, 1, 1, 1, 0. And we can actually see that this is the same as, oh, we haven't done this addition before. So I'll just do the addition again. So first bit is 0, second bit is 1. Then if we add 1 and 1, we get a 0 with a carry. And then we have 3 1s, so we'll have a 1. Oh, well, I guess I'm putting that in register B. So 1, 0, 1, 0. And so 1, 0, 1, 0. And then register B will be 1, 1, 0, 0. Oh, wait. Register B will be 1, 1, 1, 0. So I guess I did that wrong. Let's redo that.
Oh, yeah, I think you got an output and register. Yeah.
Oh, wait. Yeah, you're right. So it'll be shifted left.
Yeah. Wait.
like this.
Okay, yeah. So it does come out to 1010.
So yeah, I'm pretty sure this is the same as this row here. So we can just add them, like we can just keep our addition from that.
Yeah.
And it'll be a 1. Okay. So now if we copy these values into the current state, so 1100, 1100, I guess it's 3 ones. Yep. And then, so a shift left would mean that we lose the first bit again. So it'll be 1000. So register A plus will be 1000 because it got shifted. Register B will stay the same, so 0. And we can just do a simple addition. So we'll have a 0 in the first bit, then 1 and 0 is 1, 1 and 0 is 1, and then 1 and 1 is a 0, and then the carryout will be 1. So this is, I guess we didn't need these last 2 rows, but this should be the entire table that you have to implement these instructions using the given table here. And I have a solution here. So this solution uses register A and register B as zeros. But like we said before, if you don't know the initial state of these, you can just have them as X's. And then also, like I said before, you can have this MSA as a 1, 1 and eliminate the need for this row here if I could draw straight. So if you're trying to reduce on instructions or rows, I would say that make sure to use both, make sure to keep track of what you want in register A and what you want in register B, because moving data around is going to cost you a lot of rows in the end. Okay. Do you want to talk about shift registers with me?
Would you mind talking about them? I just like
Oh, yeah,
I
sure.
didn't prepare anything.
No, it's fine. Okay. So this is a shift register, right? I don't know if you guys learned this in class, but it's a array of D flip-flops that basically allows us, you'll use this in micro P if you take it to have serial communication, but you do also need to know it for digital logic. If we have a number come in like 1010, the clock is going to cause this output to be shifted just using the logic of D flip-flops. So it'll be 1 0 1 0, and then the input byte will be a 0, unless we use obviously like S or R to like change the specific input bit. So this is how a shift register usually works, and it's how when I was taking this course is what I was thinking when going into this lab. But this is actually not the best way that we can implement a shift register in the way that we want to use for the RALU, or some people like to call it a RALU, but I think that's kind of funny. But so this is a typical shift register, and if you're ever asked to make a shift register in the future, you're probably going to build something like this. However, this is a MUX, and we can actually implement a shift register with a MUX, which will come into play in this lab. So if we had some instructions, so if we think back to like Daphne's example from before, if we wanted to say like when S0 and S1 are both 1, 1, we wanted to shift something to the left 1. So shift left 1. I'm just going to abbreviate it. So, and we had some operations, let's say here, and we had a bus like X4 dot dot 0, right? That has our data that we wanted to shift. So what we can actually do is if this were to represent the 4th byte, so let's say X4 is represented by this
You
MUX.
probably want to do X3 to 0.
Oh, yeah, you're right. My mistake.
Then X3.
Yeah. So yeah, X3 through 0 would represent 4 bytes. So this represents the most significant bit, right? And on our shift instruction, we want if we think about a shift, right? If I had X3, X2, X1, and X0, a shift moves this byte into this byte, this byte into this byte, this byte into this byte, and ground G and D into this byte. So we can actually just route x3, x2 to this signal here. So in 1, 1, we'll have x2 come out, which actually means that we'll have x2 here, which is exactly what we want. And let's say we wanted a shift right. Shift right would be like 1, 0, yeah. So that would mean that we have ground, G and D, coming in because this bit comes out. So we would just have ground on this signal here. So using this functionality, we can represent a shift register using a mux. And that means that we can actually have an additional functionality without needing more flip-flops. And again, the point of this whole class is how can we create something using the least? So by utilizing mux and their selectability, we can actually remove the necessity for having an external shift register.
Yeah, I guess one thing also is we're making an assumption here, which is we're doing logical shifts and not arithmetic shifts.
Yes,
So
that is true.
yeah, the previous example would be good if you needed to if you wanted to like loop bits back around, like x0 would go to x3, a loop around like that. Or you might need like a more complicated setup if you're doing something like you want to preserve, like you're doing 2's complement and you want to preserve the sign bit, which would be x3 in this case, then you would just need to adjust this. This is specifically for the case, which is probably what you will most likely encounter in this class, where you just replace the bit going in with 0 or ground, or the bit going out with 0 ground. The next thing, can I have a chair?
Go ahead.
Thank you. So one of the things you're going to have to do in this lab is, like I talked about before, you're going to have control words, which are the collections of MSA, MSB, and MSC. And you're going to need to, you only have an RALU, but you have like input buses to control it, but you don't have a way to like control it without like manually changing each bit. And so what we're gonna do is you're going to use your DAD to kind of simplify this process. So instead of having to like use switches or something and then select MSA, MSB, MSC on the switches, you can use the pattern generator in waveforms, which allows you to set patterns. And so you can kind of copy paste directly from your table. So it'll be something like you'll have a table with rows of MSA, MSB, MSC. And what you can do is you can copy that table directly into the pattern generator. This is something I didn't know, so I kind of just wanted to show an example of like how you would approach this. And something else I'm going to go over is it'll help like verifying that you're copy pasting into the correct row if you have some sort of count next to it. And you could use like the row numbers as well, but I just wanted to show a formula for doing that if you're like have multiple things on a sheet and you just want to see where it is. So let's see, because you might be like off by one if you have like a header column. So let me change, I'm going to share like this screen. Okay. So I have a table here and I put like some nonsense data into this. This is I just like put random zeros and ones in this table. But the point is to show that you can do this arbitrarily. I'm not completely sure if this will work if you have it set up so it's like 0, 0. Like so I guess I would have to set this as text. Let's see. Like if you had it set up like this, I'm not completely sure if it would work. But you'll be able to verify it if you try it yourself. So let's open up waveforms. I'm just going to go through the process of like setting it up. You're going to go to patterns. I'm going to remove this so that you can see the process. You need to add a bus, and you're probably just going to want to use digital IO inputs 0 through 7, or I guess 7 through 0 if you're going by by that. You need to be very careful about like getting the orientation of these right. Like you should be connecting DIO, like you should at least know what DIO0 is going to, and you should, because it can get confusing with like I guess the endianness of it, like the order of these bits, like high to low or low to high, but this is just something to look out for. What There are two ways you could approach this, in my opinion. So the first thing you could do is you have to, okay, let me also, you have to set the type to custom, and then you click here, like to the left of output or TS is where you have to click to set the pattern. And you can like kind of expand this window. So anyway, there are two ways you can approach this, which is you can either set the patterns for this entire bus at once, like the entire control word, which is MSA, MSB, and MSC combined. And this might be easier if you want to save time, like you're just copy pasting an entire row from the sheet at once. The other thing you could do, and this is what I did because I was like manually entering the bits one by one, is you could also group it as, I think I'll have to remove this buzz, but you could group it as like, let's say you can rename this to MSA, make another one for other, let's see, I have to remove this one, put this in. So we could say this one is MSB. And this is slightly off, to be honest. It's
I don't
am I
remember
missing
which
it?
were which.
What?
I don't like remember which lines were what. If you just have like, I feel like if you just have three and like 2 and 2, you should be fine.
Yeah, 3, 2, and 2. I was okay. It comes out to 6 signals, so like I guess
Unless would that mess up like the copy and paste?
um I don't think so. I think I just accidentally put 8 signals in the first like
Oh,
thing I did in waveforms, but if you do 2, 2, and 3, I guess that might also help you verify you're doing the correct number of things. So what I'm saying is um you can either set the pattern for the individual multiplexers, or you could set it for like them all grouped together. It's really up to you. I think it's a little bit easier to verify and like debug it if you do it with individual groupings instead of like um instead of all together, because you might like wire DL4 and like you meant it to be MSC0, but it's actually going to like MSA1 or something. That's kind of all I really have to say about it. Yeah. Was I not sharing my screen?
no, you were.
I was?
Yeah, I was watching on the.
Oh. Did it stop sharing?
It's showing Excel.
Oh. Wait, was it showing waveforms though?
Yeah.
Oh, okay. Okay, I got a little worried, but that's good. Oh, I see now. Okay. This, let me close this and I'll start sharing the presentation again. Okay. Um, I guess this isn't too directly applicable to the lab, but I just wanted to talk about some of the applications of this because I honestly think it is really interesting. Like, it is cool to make half of a computer, which is what you're doing now. So, like I said earlier, the thing that you're missing from making this like a complete computer is a way to control the instructions without like yourself in time having to send over signals from your dad, or you could do it by hand as well. What you're going to do in Lab 6 is you're going to expand upon this RLU and you're going to design a way to translate opcodes. So you might have a code that's like 0010, and you're going to translate that to like a control word like literally like you made in this lab. So this might translate to adding two things together. Oh. So this is opcode for adding. I think this holds both of them.
Yeah.
Yeah. And another thing I wanted to point out is the better that you understand the system that you're making right now, as well as the system that you're making in Lab 6, the easier it will be to understand how to expand on it. And expanding on it, you're going to need to do hardware expansion at some point in this class. So I would really take your time, try to understand like how all of these things relate. Try to understand like the timing simulations for this, because you'll have to like annotate your simulations and everything, but like really try to understand how everything fits together. Another thing I wanted to mention, this is you're going to have to expand the block diagram for this. And if I remember correctly, that was basically like you should
For
have
this lab or for lab 6?
for this lab, like you have to make a PDF of this RLU, but like I think what you have to do is you have to make labels for these internal signals. Sorry, this is like, let me remove some of this nonsense. You should have internal labels for these signals, and you should expand buses where it's like relevant to expand them. And that's kind of up to you. But just to make it clear, like what the expectations are for that, it should be fairly similar to this block diagram, but yeah. Does anyone on Zoom have any questions? And you're welcome to ask in chat as well. Yeah, I guess
I
not.
had some stuff to say.
Okay.
So, that's a cool trick you had. I did this. For this, I had a couple questions in my office hours about how to draw the functional block diagram. So I think I don't know if it's part 1 or part 2, you have to draw this. So my easiest way of saying this is it's going to look like your Quartus. So, right, it's a bad thing to say, okay, let me build it in Quartus and then make the functional block diagram, but they should look identically the same. So what you're going to end up drawing is draw out all of your muxes with all the lines going in, all the lines coming out, all of your select lines. Draw all of your like logic gates, like your ands, your ors, your nots, etc. Draw out like basically all of your signals for the functional block diagram and actually think out what it's going to look like. Because either you can do it in Quartus first and then draw afterwards, and you're going to have a headache when it doesn't work in Quartus, or you can draw it first and then build it in Quartus, and then everything should work in Quartus. And then another thing is, I would say, become like get good at using buses. So when you go to do Lab 6, you're going to have a lot of inputs that are buses or outputs that are buses, and you may have lines that or like signals that aren't as a bus. So you may have to go back into your RALU that you made in this lab and change some of those signals to be buses. Also, you may need to change your decoder down the line to use bus signals as outputs instead of only as an input. So I would be like either now try to use buses as like a prelude or be able to use buses in the future because at some point you're going to need to use them.
Right.
Oh, and then I went over this. I think I tried to in the Lab 3 help session, but use wires when you're able to because the function called a wire just allows you to hook a single input to an output, to a bus signal. So that allows you to actually transfer from just single inputs to bus signals.
Yeah. Yeah, that was a good overview of that. Another thing, like this just came to my mind recently, but I know that some people have had trouble, and I had trouble with this when I was taking the class, with weird things happening on your PLD. Like you might see like random signals, like random lights on your hex lighting up, like random LEDs showing up, and it might sometimes, in my case, it would like slightly interfere with the things I was trying to actually output to the display. My theory, I'm pretty sure this is what's like this might at least help your issue. Like it's something to try for having issues with that. It says to like have output pins for like many of the internal signals, right? So you can actually like debug them. But when it comes to like actually programming to your board, it would be best to remove these signals because like I think that there is some issue with you normally set like unused pins as tri-stated and quartus, right? But again, this is not completely verified. But I noticed that it appeared as if some of the things selected as output pins were being assigned or like being outputted on like random pins, and in this case it was like on the hex display of the D10. What you can do is this is something that I saw in Lab 7. You're given a BDF to work with, basically, or you're given a Quartus project and it has two BDFs in it. One of them is for simulation, one of them is for programming. Something you might want to try just for the sake of programming on your board is making a separate BDF and removing some of the extraneous output pins from that BDF. You can right-click in your file explorer in Quartus to set it as the top level entity so that you can switch back and forth between them. So if you're having issues with anything related to like outputting to the D10 board, if your simulation works perfectly, try doing something like that if you don't want to. And you can either remove the pins in your BDF or make a new BDF to program to.
Okay, so we
yeah.
have a question. So
Oh, yeah, question.
for the cout output in section 2, should it rely on the sum function is selected if it is selection 1? In a document, it says something that makes me think otherwise.
I think it is always outputted regardless of whether sum is actually selected or not. Because like the cout itself isn't multiplexed. Like it is just a signal going out directly from like the adder implementation of it. So like, I mean, it doesn't really matter as long as you're not trying to use it, but it will like change based on the values of A and B, whether or not you're selecting the sum function.
Yeah, it might be easier to see once you build it in Quartus that you just connect the cout output from the 4-bit adder to the output. So the 4-bit adder is always adding, no matter if add is selected.
Yeah.
And so that's why, like, when I went through the table, I was always checking the cout because it'll always happen without you even selecting it, and it'll even happen without a clock.
Yeah. And complexity wise, like you would have to introduce an additional like multiplexer with like probably with the MSC as well as cout to like determine if you're going to output like cout or not or something. Like what I mean is it'd be really complicated to make the behavior to like be determined on whether the sum function is selected. So it's fine to just like leave it as the eternal output from the adder in Quartus.
So we have another question.
Okay.
For the presets and pre-clears and the flip-flops, do we have to worry about resetting them at some point?
Do you have to in the
I'm
in the
assuming they're talking about the flip-flops like to go from like register A to register A plus.
okay. So like the preset pre-clear for them?
Yeah. I don't
What do you mean by worrying about resetting them? Like you'll probably set them to 0 at the beginning of the lab, but or at the beginning of your simulation.
So
About the register bits. I was just confused, like, so you mean like resetting them during the simulation? I guess we probably should look at the lab document then.
I'm
But
thinking it's probably just like you have a start signal and you start it at 0 and
yeah.
then you don't use that for the rest of it. But I need to check.
Yeah, I know I didn't use any presets and clears during the simulation. Since you should be handling all of that like with like you're being tested on your ability to handle like using the instructions to put things into the flip-flops. You kind of already did like presets and
Yeah,
pre-clears to the counters, so
there's no start sync, so you don't
yeah,
have to worry.
you don't have to worry, yeah. Because yeah, I don't even know if I had something set to them, so I would say don't worry about it unless you see something that says otherwise, but I'm pretty sure it's not. Um, yeah, any other questions for wrap it up? Well, we can just leave it going until late if you guys come up with a question
Yeah.
and you feel like asking it to us. But good luck on your lab, everybody.
Good luck.
Yes, I hope you have an enjoyable break, even with this looming over you a little bit. Remember to start the lab 5 like state machine, like state diagram, because I think Friday you have one day where you can get Schwartz to like look over it, and it's really helpful. Like you should totally do it. So yeah.
I'd say come to the exam reviews. There's an exam review held by us on Tuesday, and Grant is having another one on Thursday.
Yeah.
And if you can, try to review the exam. The practical is going to only be tested on labs 1 through 3, so don't worry about this. And then also, try to, like Daphne said, try to do your ASM over break for, I know it looks a little bit ahead for lab 5, but getting that help is going to save you on that lab. I had Schwartz look at mine and I almost did the whole lab in like 7 hours, I think. So
Yeah. Yeah, like it's not a complicated lab. It's just like whether it functions is going to be determined by whether you made that state diagram correctly. It is really important. And like it's not that much work otherwise. You could probably knock both of them out over break if you wanted to, but yeah. Yeah. Is there anything else? We were going over the 2019 exams, right? Like
yeah,
we're doing fall 2019 or we're doing summer 2019. So I think it would be useful to try those out before you go over them. And we're doing summer 2019 if you go to that one on Tuesday.
yeah. I would say like the biggest thing is like reviewing for exam 1. I didn't do the exam before the help session, and so I didn't really get that much out of it. And so also, if you want to do any exams on your own and are looking for answers, come to office hours. You can give us the solution and be like, hey, is this right? Then we can look at the answer, say, hey, this needs a little bit of work, or yeah, that's good.
Yeah, like it's really good to have that feedback before you actually do the exam. And like I guess I always thought that we wouldn't be able to look at the solutions, but the TAs really or the pies really can help you with that. So please come to office hours. Yeah, we have 2 more minutes. Just yeah. Thank you for coming.
I would say also try to make your BDF clean. So if you do part 1 and then your BDF is kind of messy, when you go to do I don't know if it's part 1, part 2, but when you make the ALU and your BDF is messy and you try to make the RALU, your BDF is going to get really full really quick. So I guess try to like keep all your inputs together, make your muxes nice. So it'll look pretty nice.
Yeah. Yeah, use the rectangle tool to
I didn't know
section things.
I didn't know there was a rectangle tool until like a couple days ago.
Yeah,
But it's
so
pretty
nice.
clutch.
Yeah. Okay, well, I'm gonna end the Zoom now, but good luck.